Maths through the ages, a general history for teachers and others. Others being students or non-students and non-teachers. Office workers. Today we'll be talking about mostly high school stuff. Note, I am a middle schooler. Well, I will be starting high school in a few days. But that doesn't count. Let's start off now. Shapes by numbers, coordinate geometry. Coordinate geometry itself is pretty easy. Like, I'll show you it on my laptop on Desmos. This is coordinate geometry. Go ahead. Oh, that's not my laptop. Yeah, here we go. Go ahead, and you put in little bits of coordinates. This kind of stuff. 0, comma, let's say 5. And here's a little coordinate right here. There's a coordinate right here. And then let's say you go ahead and make a little graph. Y is equal to, say, 5x plus 7. Oh, yeah, here we go. Here's your linear equation. And this is Desmos teaching you about coordinate geometry. But essentially, all you need to know is that coordinate geometry is written like this. There's like brackets, comma in the middle. This side is your x coordinate, this side is your y coordinate. As earlier mentioned, my 0, 5, my x coordinate is 0, my y coordinate is 5, so on and so on. It can be negative, negative 5, and there are several quadrants. Like, see this area? This is known as the first quadrant, meaning because its coordinates are positive values and positive values. This area is known as the second quadrant, because its values is the negative and the positive value for y's. This is known as the third quadrant because it has the negative x value and the negative y value. And this is known, I just realized this looks like 4. And this is known as the fourth quadrant because it has a positive x values that has a negative y value. And yeah, you can see this, just memorize this, it's pretty easy to do. 1, 2, 3, 4. And now we are here with impossible, imaginary, useful, and complex number. Like I promised you, I'll be talking about negative numbers and those like complex numbers. And now here we are. Square root of negative 1. Like, what is it? Even Desmos calls it undefined. Unfortunately for Desmos, we humans like to make things defined, so we decided to just call square root of negative 1 as I. Why? Imaginary number, which is terribly named, by the way. It's not imaginary. But it's not impossible as well, too. It's very useful, too, because this represents square root of negative 1. You square it, and you pretty much get negative 1. And this has helped us make several solutions, because, there's a rule in quadratic equation where if you, make a quadratic equation in the form of, ax squared plus bx plus c is equal to 0, and you find that b squared minus 4ac is less than 0, well, then you got an undefined equation. Well, instead you could just make a imaginary solution, a useful I solution, a complex number solution. Yeah. And then we talk about sine and cosine. Sine and cosine works like this. There's a right triangle, boom, boom, theta. And let's see, what else can we do? Let's just call this theta. Then your sine will be your opposite divided by the hypotenuse. This. Your cosine will be your adjacent divided by the hypotenuse. This. And your tangent will be your opposite divided by the adjacent. This. Or you could just memorize SOHCAHTOA. This is way easier to memorize and sounds way better. But in the end, of course, we go ahead and learn something about them. That these guys are all doofuses. Sines and cosines might be useful, but by itself, there's not much practical usage you can do it other than finding heights of stuff and solving math problems. Sine and cosine by themselves and tangent by themselves isn't that useful. You have to use variations of those sides, so you could just use combinations of them as well too. This is where secant and cotangents come in. Learn those by yourself. This is just the basic stuffs. And then we talk about non-Euclidean geometries. Non-Euclidean geometries, one of the most strange new worlds ever. And in the end, of course, non-Euclidean geometry is mostly a type of geometry that differs from Euclidean geometry, right? Rejecting one or more of those Euclidean postulates. Like if you go ahead and reject the parallel postulate of Euclidean geometry, which is parallel line, these two are parallel, then this angle equal this angle, this, which is also equal to these angles, and then these angles will be same, like that kind of postulate. Well, then you go ahead and learn different geometric properties. Like non-Euclidean geometry is study spaces that are not flat, but are more like curved. Unlike Euclidean geometry, which is more like the flat kind of guy. Hyperbolic geometry and elliptic geometry itself is included here too. But I'm not here to teach you math, I'm here to tell you about math. And then we have projective geometry. Projective geometry itself is a branch of math which is focused on geometric properties that have undergone under projections, according to AI overview. Those used those perspective drawings, the kinds that the artists use to go ahead and use these curves and stuff. You go ahead and learn curves. Leonardo da Vinci used projective geometry to go ahead and draw, say, the Mona Lisa. It's this kind of stuff. You go ahead, you learn the projective geometry, and most people usually use this for their art classes. My art teacher told us about this because apparently it was required. And artists have to learn this, and people go ahead and learn all this to make their art look a little more realistic. Alright, and now, next time, we have to talk about making sense of data. Apparently, statistics. Statistics is one of my weakest points in mathematics, arguably so. Statistics itself is just data analysis, graphs and stuff. You read graphs and you interpret the graphs, which unfortunately I'm terrible at. Don't blame me, but I'm starting to learn statistics, and I might get a 4. And next then, we have electronic computers. Electronic computers, like the ones I've showed you in my videos, have went ahead and helped us improve our mathematical understanding and capabilities. It helped us calculate 300 trillion digits of pi, and it helped us have programs such as Desmos, which could just do stuff for us. It helped me cheat. I emphasize the word, I air quote the word cheat because it's legal on the DSAT to do stuff on the DSAT and do it way better and without me needing to learn anything. The arithmetic on reasoning, Boolean algebra. Finally, Boolean algebra. Boolean algebra is just a set of algebra that relies on binary numbers. The ones that computers use, 0, 1. It's how computers do math. Essentially just the same as regular old algebra, but computers. Alright, then we have infinity and the series of sets, which helped us categorize everything. You could make a set about everything, including the set itself. And you could essentially go ahead and create different sets, like positive sets, negative sets, sets of 1 all the way to 10, or you could just create sets of objects. And then finally, we have the tangent function, which I personally already talked about the tangent function earlier when I talked about the sine and cosine. Tangent works like this. Tangent itself, it's not the right triangle tangent SOHCAHTOA tangent. No. Tangent is like a line that barely touches the circle. Why I emphasize the word barely touch is that it only touches the circle at one point. And if you draw a radius from the center of the circle all the way to that one point, you would create a right angle, which is why tangent lines are always 90 degrees towards at least one radius. This is apparently useful for math problems like this one. This is featured on the DSAT, so if you're taking the DSAT, take notes. And then we have logarithms. How we humans like to simplify stuff from whole numbers all the way to those to multiplication. Multiplication is technically just repeated addition, and squares of stuff, powers of stuff is just repeated multiplication. Well, to simplify that kind of stuff, simplified powers, we decided to use something called log. Kind of works like this. How exponents themselves will go ahead and the c at the top, we have a base, we have a value of that. Well, in logarithms, we go ahead and switch it up. The base logarithm to the power of a base to the b. Essentially, we're asking if a to the power of what is equal to b, and then we eventually find that what as c. If you get it, great. If you don't, well, watch that again. Then we have conic sections. Euclidean geometry, plane geometry, except now we're combining 3D with 2D. You make a cross section. You make cross sections and you find what each one of those look like. This is apparently called the hyperbola. This is the parabola. If you put a plane in different ways through the 3D object, well then what would you get? And then finally, we're going to talk about irrational numbers and then tangents to the derivatives. Irrational numbers themselves are pretty easy to talk about too. Like e, pi are one of the most famous of those irrational numbers ever. Unfortunately, e is not that famous as its counterpart pi, and well, it itself is also irrational as well too. I already showed you the pi's irrational numbers, but the mathematical constant e, which is Euler's number, well, it's an irrational number. It's just an irrational number that goes to show how things work. Irrational numbers themselves, people really hated because the irrationality. The Pythagoreans themselves went ahead and hated irrational numbers, which is why they allegedly killed someone for saying square root of 2 is irrational. Well, they really hated irrationality. Also, I don't think killing someone is the way you do it. Then we go ahead and figure out and accept, eventually, that irrational numbers exist. And we make these new laws. Like, if you can't write a decimal as a fraction, well then, it's an irrational number. If it's infinite and no repeating values, no pattern of repeating values, well then, it's definitely irrational. And then I already told you about tangents and the derivatives, so I think that wraps this up for today. Oh, and remember in the last video when I told you about that riddle about 1 plus 1 is equal to 6? When does this happen? Well, this. 1 plus 4 plus 1 is equal to 6. It's a riddle, okay? You only add one line to go ahead and turn 1 plus 1 is to 6. And this is how you do it. Pretty good math riddle if you ask me. But until next time, my fellow peeps, I hope you guys enjoyed this math journey as much as I did. So, until next time, 希望好 peace. Bye bye! Highlight time over. Time to reflect.